Alright guys, so this is the handout I was talking about in the last video, and hopefully you were able to obtain a copy and you got these Lewis diagrams all colored in. Okay, so there's a Lewis diagram that's sort of the first part of predicting molecular geometry. So, a little bit of background here. This is Miss Turner's handout, so these details come from her. Many properties of substances are determined by the shape of its molecules, melting and boiling points, hardness, viscosity, and volatility, so all those physical properties are based on molecular geometry. Quantum mechanics can help explain how atomic orbitals overlap to form bonds using valence bond theory. However, a much simpler and more reliable method to predict molecular shape is the VSEPR theory of Dr. Ron Gillespie, an inorganic chemist from McMaster University in Hamilton and your grand teacher. Now, actually, so Dr. Gillespie was one of Ms. Turner's professors when she was doing her degree at McMaster, but he wasn't my professor. Ms. Turner gave me this handout though, and even though I knew about VSEPR theory before I met her, I did learn a lot from her, so you can say that he is your great grand teacher based on sort of the trickle down of information there. So VSEPR, which is obviously not how you would pronounce this order of letters, but that's how we say it, is an acronym for valence, shell, electron, pair, repulsion theory. And it uses the interactions between electron pairs to predict the geometry of the molecule. Okay, so we want to remember that electrons all have a negative charge and they repel each other. Okay, so electron pair repulsion is a really important concept here. So let's look at our first example here. A lot of the information has been filled in for us. So our first example is the phosphorus trichloride molecule, and the Lewis structure you get for that should look something like this. And once you have the Lewis diagram done, the next thing you want to do is total up the pairs of electrons around the central atom. So here, phosphorus is my central atom. I have 3 bonding pairs, so that's what this represents. And then one, I'm going to call this non-bonding pair, from here on out a lone pair. So in total I have 4 pairs, and then they're broken down in this way. Okay, so when I have 4 pairs around my central atom, like I do in this case, that gives me a tetrahedral basic shape. And we'll go through a few different basis shapes as we go forward, but for now just know that anytime you have 4, your basis shape is tetrahedral. Okay, and when you have a tetrahedral shape, you're going to start with your central atom, and then it has 4 things coming off of it. And when we're drawing our 3D diagrams, if something is being drawn in the plane of the page, we just draw it as a normal stick. Okay, so we're going to draw our first bond like that, and our second bond like this. Okay, and then we're going to imagine there are 2 more things that I have to draw. One of them is going to be coming out of the page. I'm going to show that as a wedge, like this. So the wedge means coming out of the page. And then I have one more thing, it's going back into the page. I'm going to show that like this. Okay, so that's the beginnings of a 3D diagram for something that has a tetrahedral basis shape. Now in this case, I'm going to draw my chlorines in these positions. Okay, but then actually the last one is filled up with a lone pair. I don't need to include that in my 3D diagram. So I'm going to erase that last one. And this is my complete 3D diagram, okay? So I don't need to include the lone pairs when I show that. But I do want to show something that reflects the 3D diagram. Okay? Now, let's talk a little more about this idea of a tetrahedron. So I used the molecular model kits to build some of these shapes. So this is what a tetrahedron looks like from the top view. And then you can see as I rotate it, okay, so I've got 4 things coming off my central atom, and they're all perfectly evenly spaced around it. Okay, so this is a tetrahedron. Now, in that case, when everything is perfectly spaced around a central atom, okay, so everything repels equally, the angles in a tetrahedron are 109.5, so that's why you see this number right here. what goes on here, and we'll talk about this in a little more detail later on, but what actually goes on, the lone pair up here, it's a little more repulsive than the bonding pairs. So we actually end up kind of, if you can imagine, you kind of squish if this that I'm holding up here is the lone pair, and these are all the bonding pairs, the lone pair is a little more repulsive, so it kind of squishes everything down. You can see I'm trying to kind of squish things, but they're a bit strong. Okay? And that means that those angles between the bonds, they get a little bit smaller than the typical 109.5. So the angles in a tetrahedron where you've got the lone pair in one position are about 107 degrees. Okay? Although using this idea, less than 109.5 is perfectly reasonable as well. Now, I know this seems a bit irritating, but IB does have an expectation that you'll memorize, especially for the tetrahedral basic shape, the bond angles. Okay, so there is a requirement that you'll do that. Okay. Now, this first example was a little bit of a tricky one. It kind of just jumped right in there. We are going to develop these ideas a little more thoroughly and a little more systematically as we go through the rest of the examples. Okay, so the next thing I'm going to look at is beryllium dichloride. So that's an example of something with a smaller or a contracted octet. Okay, so beryllium is okay with just these 4 valence electrons. So I can see around beryllium, I really just have 2 bonding pairs and no lone pairs, so 2 pairs in total. And I'm sure you can guess, if I have just 2 electron domains that are repelling each other, the way they can be as far away from each other as possible is to make a straight line. So the basis shape here is linear. Okay, and then I actually don't need any sort of fancy wedge and dash notation because these are both in the plane of the page. So when I draw my linear diagram, I'm actually just going to do it like this. And the nice thing about my 3D diagram, it doesn't need to include the lone pairs. So this is perfectly fine. Okay. Now for the molecular geometry, you'll notice that in the example we did before, the basis shape was tetrahedral, but then we had a more specific molecular geometry based on the fact that there was a lone pair. In the case where there's no lone pairs, like we're seeing in this example, the molecular geometry matches the basis shape. So I can actually write the same word right here. And then hopefully you know that when you have a straight line, that's 180 degrees. So the bond angle here is 180 degrees. Okay? All right, last example on this page, we've got boron trifluoride. And here, again on the boron, we've got a contracted octet, only 6 electrons. It's cool with that though. So we've got 3 bonding pairs, no lone pairs there. Okay, and in this case, everything's spreading easily. It's going to stay in the same plane though. So the basis shape here is called trigonal planar. Okay. And this is another pretty easy one to draw. I don't need any wedges and dashes. I can just put in my central atom and then I'm just going to show everything approximately equally spaced around it. And I don't need to include lone pairs in my 3D diagram. Okay. Once again, I have only bonding pairs, no lone pairs, so my geometry, my molecular geometry, can match the name of my basis shape, trigonal planar. Okay. And then you can imagine all of these bonds are spreading evenly in space. So a full circle would be 360 degrees. We've divided that up into 3. So the bond angles here are 120 degrees. Each of those angles is 120. All right? So that's the first page done. And before I pause this video, so I am going to stop it at the first page here, I want to just show you the molecular model for something that's trigonal planar. So you will see that it's a flat plane. Okay, and then everything's evenly distributed in around those 360 degrees. So those bond angles there are 120 degrees.